Okay, so let's look into the models of enzyme action. So how exactly do enzymes and substrates come together? So the most traditional, and for the longest time, this was the main model used for enzyme substrate complexation, it's called the lock and key model. So the enzyme is like a lock on a door. The enzyme is like a lock, and then our substrate is like a key. So what was thought about this is that the active site of an enzyme is very rigid. It has one specific shape. It's not flexible at all. And then the substrate specifically fits into that lock. So as you can see, you'll see a little bit different things lower, but the hole in the enzyme here is the perfect exact fit for that substrate, which in this case is a rectangle, to fit in like a lock and key. So everything is very fixed, no shape, no conformation changes at all. Everything is very rigid and non-flexible in their structure. So this is not actually the full, I guess, what we think of now. So this is the extreme. So we now recognize enzymes as more dynamic and flexible. So you will hear, if you talk about enzymes and anything with pretty much any kind of biologist in general, they will talk about the lock and key method because that's the most, I guess, the easiest way to understand it is that there's a specific key that fits in the specific lock. However, this is not fully true. So going on into the other two models, it takes into account the dynamic structure and flexibility of the enzyme. So we have induced fit and conformational selection. So let's start with induced fit. Induced fit starts with the substrate and the enzyme meeting up. So they come together, and you'll see, like in this cartoon, the pocket doesn't perfectly match our substrate. But after they form their enzyme substrate complex, the active site and substrate will morph and form the optimal geometry. So they will come together, forming the enzyme substrate complex. That enzyme substrate complex will then be in equilibrium with the optimal geometry in order to do the reaction. So binding of a substrate induces a conformational change. That's where you get the name induced fit. Binding induces conformational change. So this is more of a dynamic model. Yeah. And then we continue on to the conformational selection. So this is very similar, but different in one key aspect. But in this conformational selection, so this enzyme is more flexible and more fluid before the substrate binds in with the enzyme. So you could have this mix of the square or rectangle version and the circle version of the enzyme. It's flexible, it's constantly fluid in between the two. There's multiple forms of the enzyme, only one shape interacts strongly with the substrate. So this circular shape would not interact very well with this rectangle shape, whereas the rectangle enzyme would. And so the thought here is that when the enzyme in its flexibility forms into the appropriate structure, it will then have a higher interaction or higher chance of bonding with your substrate in order to form that substrate enzyme substrate complex. So in this case, substrate only binds to the active enzyme and the shape matches when the shape matches. So again, this one's also dynamic. Dynamic in that things change as we go. It's not everything fully rigid. So let's consider this question. What is the difference between an induced fit and a conformational selection models? So how are these two different? They both have an enzyme changing shape in order to make the correct enzyme substrate complex. So what's different about them? Well, the big difference is when the conformational change happens. So for example, in the induced fit model, you bind first, then the enzyme conformation changes. Whereas in the conformational selection, the enzyme is fluid and changes its conformation first before binding happens. So it's whether conformation changes before or after binding.